Well, let's start. So today for our seminar we have Stephen Chen, who is a postdoc in Columbia University, and also has been a postdoc in the Institute of Advanced Study. That I didn't know, but it's the institute where Einstein used to work. He obtained his PhD in Berkeley, and he has worked in cosmology, large-scale structure, effective field theory, and is the author of the velociraptors code, which does perturbation theory, both Lagrangian and Euclidean. And today he's going to talk about cosmic shear. So.
Thanks. Yeah, thanks for inviting me. I've been really enjoying being here. Well, except for the past 2 days where I have food poisoning, slightly less fun. Yeah, so I'm going to talk about some recent work. I've worked a long time in trying to do various cosmological observables using analytic theory, like many of you here as well. And recently I became interested in the idea of doing also weak lensing using analytic methods. So today I'm going to share a little bit about some progress we've made. And I'll explain why I call it a doubly effective view. We kind of use the EFT effective field theory twice as we go. So, okay, so yeah, I'm gonna so the overview will be the element of the talk as follows. I'll begin by giving an overview of weak galaxy lensing. Then I'll argue that we can actually model cosmic shear as weak lensing using analytic methods. As the answer to the question, is cosmic shear perturbative? Is yes. And then I'll explain why we can do that. So I'll explain how we can use techniques from effective field theory to really rigorously construct these observables from a theoretical standpoint. And then finally, I'll present the results on applying these to data. So just to give the obligatory state of cosmology slide that every cosmology talk has, we're kind of at, I think, quite an interesting time in cosmology. That we have this standard model of cosmology that is very well predicted many things. For example, really all the details of the cosmic microwave background, more or less agreeing with also our observation of galaxies and their clustering, the late universe. But as our data has become better, many cracks have begun to emerge in the standard model. You may have heard the most famous one may be the so-called Hubble tension, that is the measurement of the local expansion rate H0, where we see a significant discrepancy between measurements made in the late universe and all these points here and what we infer the cosmic microwave background. In the standard model of cosmology, also from galaxy clustering. Actually, embarrassing, it also looks like there's some discrepancies. Then there's, of course, some recent developments, as I'm sure you've heard from your local colleagues here, where the dark energy spectroscopic instrument DESI, when combined, using its latest data, combined with CMB cosmic background and supernovae data, seem to show a preference for dark energy beyond the cosmological constant. That is in tension with the standard model of cosmology, which is the constant dark energy to this point here. And finally, we have another tension that is, has a bit more of a questionable level of significance, but the so-called S8 tension, where the amount of matter clustering as measured to weak lensing surveys, which I'll talk about in this talk, seems to also be in some slight, maybe 2-ish sigma discrepancy with the cosmic microwave background. So it's really quite an interesting time to be looking at precision models of cosmology to really tease out these differences. And so in this talk, I'm really going to be talking specifically about cosmology via the large-scale structure of the universe. And so what do I mean by this? What I mean by this is we're really studying the distribution of matter in galaxies on very large scales. And what we care about can be really simply described perhaps in general relativity as just, for example, in this metric where we really want to study the behavior, the evolution over time, the spatial structure of the gravitational potentials, the time, the Newtonian, and the spatial potentials, and also the expansion history through the global growth rate AFT. And both of these really depend on the underlying particle content of the universe. For example, dark energy, as I showed in the earlier plot, but also the behavior of dark matter, the behavior of baryons, neutrinos, and even, of course, the underlying nature of gravity. Oh, something happened?
No.
Oh.
It's just a bunny.
Gosh, thank you. And And of course, all these things are probed by the distribution of matter in galaxies over 14 billion years of cosmic time, as you can see here in this cartoon that I'm sure you've seen. And there are many, many probes, including, say, galaxy surveys, the Lyman alpha fluorus, which probes neutral hydrogen, intensity mapping of the 21 centimeter line, which may or may not one day happen. But in this talk, I'm going to focus on weak lensing. Right? So weak lensing, of course, is the distortion of photon trajectories along this path by these large scope potentials. Right. So in particular for this talk, I'm going to show a few summary equations just so we are all on the same page. In this talk in particular, I want to talk about weak galaxy lensing, right? Which you can see in this picture is the distort. If you measure the shape of a galaxy in the sky, you don't really measure its intrinsic shape, but rather its shape modulated by the lensing, the gravitational potential between us and these galaxies. And this distortion is governed by the so-called Weyl potential, which is the average in GR of the spatial and time potentials. And in the Born approximation in this weak lensing limit, this is governed by the lensing potential, which is an integral of this potential along the line of sight. Right. So you basically weight the gravitational potential along between the galaxy and us, and this sum potential that informs us through this weight, where chi is the co-moving distance along the line of sight of the potential. So this, of course, we immediately see that this lensing potential probes two things. One is it probes the growth of structure, the formation of structure through the gravitational potential generated by the matter distribution. But it also independently also probes the geometry of the universe, because this weighting of the lensing signal depends on the distances between us and the galaxy. Right. So immediately we see that cosmic shear or weak galaxy lensing probes geometry of the universe and the growth of structure, which are then tied together, of course, through this metric as I was showing on the other slide. And then once I have a lensing potential, of course, I can get the deflection of light just by taking the gradient, the angular gradient of this thing, to get an angular deflection, which is nothing more than the gradient of this potential. And once I do this, I can get a distortion in the angle. So then any particular shape gets transformed according to this matrix, which is the identity minus the second derivative of the lensing potential. The details of this are not particularly important, but this matrix then we can decompose. This matrix, as you can see, is a symmetric matrix, so we can generically write it in such a way. And here we have two critical pieces. One, kappa here is the so-called convergence. As you can see, it lives isotropically along the diagonal, so all it does is magnify or shrink or stretch things isotropically. And then we have the shear, which is what I'm going to talk about here. The shear is our gamma 1 and gamma 2. And here in this nice plot, you can see that as I move along different values of gamma 1 and gamma 2, this corresponds to shifting this circle into ellipses of various orientations. And a nice mathematical property, of course, is that this shear is a spin 2 object. You can see that you go through one period by going one half. But of course, it's important to note that both of these quantities are derived originally from the lensing potential. So they're both kappa and gamma are really describing the same things. It's just a matter of how we measure them. And in weak lensing, we like to use the shear because it is harder to mimic a spin 2 distortion of the shape of a galaxy versus we don't really know a priori the distribution of the sizes of galaxies, which is what we would have to do if we measure them from kappa. But anyways, okay, so if we measure this, then we have this probe of the growth of structure and geometry. And so what do we really want to measure? Well, a very convenient thing to work with. Okay, I'm gonna talk about kappa now here because it's easier. The convergence is scalar, so it's going to be easier to describe its statistics. Well, but what we really want to do is to measure the correlations of the weak lensing signal on large angular scales, right? What we want to know is whether there's a correlation between the weak lensing of a galaxy measured in this direction versus that direction, because that would indicate that it's being distorted by some coherent large-scale cosmological. It'll be very convenient for us to work in Fourier or so-called harmonic space, at which we take the convergence measured at some angle theta and Fourier transform it into the convergence measured at a harmonic L. And once we do this Fourier transform, then of course we can measure the so-called power spectrum of the harmonic space power spectrum of these things, which are just given by the expectation value of kappa L times kappa L prime. The translation invariance, of course, tells us that only L equal L prime correlates. So we're really interested in this thing called the power spectrum. And in the so-called limber approximation, taking into account this angular weighting that I mentioned earlier, we get that C kappa, this power spectrum, is really an integral, again, along the line of sight, times this weighting, the lensing kernel squared, times the matter power spectrum. So these two quantities are really the most important two quantities for this talk. Where they really, here, the first one is the so-called lensing kernel. This is the weighting of the lensing along the line of sight. And roughly speaking, if we have, again, some object at chi prime, let me just come back to show this picture earlier. I'll just come back to this picture. If I have some object at chi prime, and an original galaxy that we measure at chi, at a distance chi, then the lensing kernel is just reflecting this weighting. You can see that this is an object that peaks roughly at about a half between the object and the source. And then once we have this lensing kernel, which is the weighting by distance, we also have to factor into account the matter power spectrum, which is how much matter clusters in 3 dimensions now. You can see that I've transitioned from L, which is an angular coordinate, to a three-dimensional limitum K. And these two ingredients then, when integrated together, tell me what tell me how much weak lensing clustering there is at any scale. Just to pause a bit on the so-called limber approximation. Here I've just taken, just to give you an example, a measurement of this weak lensing power spectrum from the DES survey year 3. And you can see, of course, that there's a very nice measurement of this signal over many angular scales, where L, of course, corresponds roughly to pi over theta in terms of the angular scale you're probing. And so if we stare at this equation, then the two important things for us are one that roughly at a given angular scale.
The difference on the dashed on the solid lines.
These are the two theory predictions of 2 months. One of them is to a smaller scale, one of them is to a less smaller scale. I would not trust them particularly. It's more important that the data points are. Yeah. So, I mean, for us, the takeaway from this equation is that for a given angular multiple L, we're really probing a 3D physical momentum K equals to L over chi, where chi is the distance, right? But given that, it's also important to note that this integral, which is this weight W kappa, which I'm showing here, is very widely distributed in distance. So even though the peak is about at chi over 2 between the source and the distance, we're really sensitive to all the matter clustering at the distances between us and there. So we're really, and when you translate that into this K, this means that for a given L, the fact that we're going over many chi's, I'm really probing very many physical scales. And in the end, when you do all this, conventional analyses tell us that the best constraint quantity in these analyses is the quantity called S8, which is a combination of the matter fraction omega m to the 0.5 times the matter clustering amplitude sigma. So this is kind of the best measured quantity in weak lensing, and it's the basis for this S8 tension for these measurements.
Sorry, a question.
Yes.
This lensing kernel, it was an assumption, or it was an analytic?
It's analytic. So it follows from it follows from this. So once you write down what the lensing potential is in the Born approximation, you can work it out step by step. I mean, the lensing kernel is just a translation from this potential into kind of the convergence implied in this distance. Okay. So you're just taking 2 derivatives. So yeah, you do this, and basically here, once you do this, you see that kappa is an integral in the same way, and that gives you the lensing. Yeah, thanks. Yeah, so you can see anyway. So here we're at a stage where we see that naively, what we really need to do in order to measure to model weak lensing is to really have to capture the clustering of matter over large distances and over many physical dimensions. Right. And before I go on, I just want to mention that it's really an interesting time to be looking at this because the weak lensing landscape will soon be transformed by, for example, the Euclid satellite and Rubin Observatory, both of which are currently taking data. I think there are people here who work on Rubin. I don't know if there are people here who work on Euclid, but these will both be kind of transformative experiments compared to this measurement, which is the best so far that we have. And okay, so with all that preamble. Is that not correct? Well, that's not correct.
No.
Okay, good. I was very worried. So So without the preamble, I want to talk about why weak lensing is really hard for theorists, particular. All right, so again, we have this integral of the weak lensing power spectrum at a particular angular scale L, or a particular angular scale theta, and fundamentally, this is very difficult for us theorists because angular measurements mean that physical scales are mixed. Right. So suppose I want to understand the correlation of the weak lensing scale between these two galaxies that subtensile angle theta. The problem is physical theories are always valid up to some physical cutoff lambda, right? So suppose this angular scale subtends this physical scale lambda at some distance chi, which is in the infrared in the long distance regime. When I go to the short distance to the ultraviolet, this is always also picked up by the same integral just at a closer distance, right? So naively, it seems quite difficult to model weak lensing from an analytic first principles way, given that all theories have a fundamentally work below some scale length, right? And this, you might have heard a lot about DESI from the local cosmologists here as well. And this is fundamentally very different from a spectroscopic galaxy survey like DESI, because there we get a full three-dimensional map, as you can see here, from the galaxies, which we can then convert into correlation functions in physical space, have very, very well-defined features and very, very clear physical separations in the correlation function. Whereas in weak lensing, what we get instead is a really large two-dimensional map of say, the weak lensing observable here from DES that converts into an angular correlation function, which is much more smooth because we're averaging over many angulars and many physical scales. Right, so this is a profoundly different kind of measurement than the kind of three-dimensional measurement that we're kind of used to in modeling from an analytic perspective. But of course, we're not doing this for no reason. We're not throwing away this physical information for no reason. The fundamental reason we want to do this is because by doing so, by not having to take spectra for each of these galaxies, we can get a much higher signal to noise by capturing the weak lenses of many, 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 many galaxies. And of course, then measuring the weak lensing signal allows us to directly probe matter clustering in the late universe through measuring the Weyl potential from weak lensing. Whereas when we do these kinds of measurements, we always have to go back to translating between physical galaxy clustering and matter clustering for a more complicated theoretical model. Right, so there's kind of pros and cons of both of these, but basically what I want to convey in this talk is then how we can make progress by in this column by going through this two-dimensional weak lensing. Okay, just as an aside, I'm going to be talking about cosmic shear through this spin 2 shear measurement, but in fact, it is also actually possible to do cosmology using convergence. We had this nice paper last year with Noah Saylor, where we measured the convergence power spectrum between galaxies in the DESI survey, and you can see actually very clearly this convergence power spectrum that we've measured by cross-correlated galaxies, but in fact, this turned out to be a much trickier and much lower signal to noise measurement. But just to show that the very same lensing potential, you can also prove its spin zero component in cross-correlated galaxies. So it's not all made up. All these signals actually exist. Okay, so how can we measure how can we model weak lensing? By the way, please stop me at any point for questions people already have. So I want to answer this question of whether we can indeed use analytic or perturbative methods to model weak lensing. But before I do so, it's important to give kind of the overview of what's already been done. So in my mind, there are roughly two strategies people use to model cosmic shear. And in fact, when I say model cosmic shear, what I really mean is modeling the nonlinear matter power spectrum PMMK. Right? Because the extension history is easy in the sense that it's analytic. We can work out all these things in a fairly straightforward way. I think it's not controversial how we do that. So what is really difficult is how to come up with a nonlinear clustering of the late universe where gravitational structure formation is really rather nonlinear, as given the linear initial conditions which we take as an input from inflation in early universe physics. And roughly there are kind of two ways. The first way, which I will focus on in this talk, is the analytic way, or the so-called effective field theory way, where we solve for nonlinear structure formation perturbatively order by order, the initial conditions. And the benefits of this are that it's a first principle way, it's inexpensive, relatively speaking. It's easy to generalize for various kinds of new physics. But on the other hand, it has a finite mutual convergence. And maybe the math is hard, but it suffers from not being able to go to all scales. As in the second method, where we run an n-body simulation, which is a fully nonlinear simulation of dark matter dynamics. And in this case, we can, in principle, go to an arbitrarily precise and arbitrarily small scales in the system. But of course, the difficult, the con of this is that these simulations are very expensive to run, and they're hard to generalize to they're hard to generalize to to models beyond the standard model of particle physics. For example, if we have the Seminario del Cosmología, for example, if you have dynamical dark energy, if you have dark matter interactions, is more difficult. And of course, when you run the simulations, each is very expensive, so you cannot, of course, run one simulation for every cosmology, but rather you have to interpolate between different simulations by using either quasi-analytic expression. People often use this code. The standard field is something called HM code, which is for Hamilton model. Or you can use kind of machine learning-based emulators. But there's an extra step in principle compared to the analytic method, where you can, in principle,
Is it obvious in the analytic approach where the conversions is lost?
I will get to that. That's a very good question. I'll get to that in a second. But just to summarize, those are a lot of words. Really, pictorially, what I mean is that in one approach, we're really computing these loop diagrams at order by order, from 0 loops to 1 loop to 2 loop, so on and so forth, by taking into account of nonlinear clustering, the nonlinear couplings induced by gravity. Whereas running, and when running an antibody simulation, we really capture all of these nonlinear in one step, and you can immediately form this very, very, very nonlinear structure. But of course, at the cost of being very expensive from a CPU perspective. But yeah, I'll get to your question in 1 second. But let me just motivate a bit why it may be that the simulations, which is the current state of the art, may be a bit more tricky than you might naively think. So cosmic shear, of course, has high signal to noise at small scales or at large L, where the simulations naively shine because, as I will get to, the perturbation theory and analytic methods, of course, have a finite radius of convergence, and so they may not converge on the scale that you want. But on the other hand, upcoming surveys like LSST in the Rubin Observatory will probe cosmic shear and will probe weak lensing at the 0.5% level or better, according to the forecasts. And here I'm showing in this plot, which I took from my paper with Joda Rose and other colleagues. Here you can see the state of the art for different emulators using simulations for cosmic shear. And what you can really see in this picture, I hope, is that the scatter on these simulations, even for shameless advertising, even for our state-of-the-art new emulator, is a percent at small scales, right? So there is not an emulator on the market that can reach this level of precision. And indeed, it is quite hard to imagine simulations really reaching this level of precision consistently, even within the lambda CDM, right? And so the state of the art we're at for simulation is really at a 1%. Well, and so naively, we want a factor of several improvement. And furthermore, this is only for lambda CDM. If we want to go to even dynamical dark energy, which does get made interesting, there's the cost of these emulators is exponential in the number of parameters we're probing. That makes simulations naively very, very difficult to improve significantly. Current step. And even in this case, I will mention, even in this case where we're really pushing the error bars down to below what you would need to detect a neutrino mass of dynamical dark energy within an emulator, these have been made noiseless because I'm coupling them with perturbation theory predictions, DFT predictions. So simulations on their own, it seems like it will be quite difficult to do. Yes.
Even at those scales, but bionic effects are important.
Yes, I'll get to that. Yes, people keep asking me questions I'll get to, but this is an important part of the argument. Yes.
When we finish the talk, I come to.
Yeah, I will answer this question. Yes. Yes. So that to me suggests we should think about using analytic techniques. The analytic techniques never have this problem of to what percent are they accurate. I mean, this is a very well understood problem where if I go to X order, I can reach X% precision. But how do we do so, right? So just to give a review, the alternative of doing the simulations is to say the following. If I look at this picture and I zoom out far enough, on a very large scale, it turns out that the structure formation of the universe actually behaves as the effective field theory of a gravitational fluid, right? So when I zoom out far enough, the behavior of dark matter is really quite simple. It obeys the continuity and Euler equations. And the only way you would know that something more complicated was going on was that the effective stress tensor here in this term is sourced by the nonlinear structure, the small scale nonlinear clustering of dark matter. And so it sources in this stress tensor a response to the long wavelength perturbations of the field. And that sounds perhaps slightly abstract, but this is really no different than the fact that when we study, say, fluid water, these fluid parameters, the viscosity and so forth, the sound speed of the water, are reflections of the interactions of water molecules and their hydrogen bonds on small scales. So we gain these three parameters like mu here. There's a sound speed here implicit in the equation of state, and then we emerge from this. We come out of this with an effective theory of the fluid shown here that works when we're on when we probe momenta that are much smaller than 2 pi over 1 angstrom. Right. So 1 angstrom here, of course, defines the spacing between water molecules. But we can, of course, paint a very similar picture for dark matter, where the EFT really works on scales where dark matter behaves with fluid. And what we mean by that really is that the perturbation, the mean fluctuation of the density below this momenta, which we can write roughly in dimensionless terms as k cubed times the linear power spectrum, should be less than or equal to 1. Below this scale, dark matter has stream crossing and various kind of fluid singularities, which would break the behavior of the fluid. And so this, to answer your question, so this scale is really what sets, this number being 1 is really what sets the convergence, the radius of convergence of the perturbation theory. And what you can see is that as I go closer and closer to the present, I go from the early universe to the current universe, this threshold is being crossed at a larger and larger scale, which corresponds to the breakdown of the fluid picture at larger and larger scales as the universe becomes more linear, and as these non-fluid characteristics which are being captured in the perturbative limit by the fluid parameters become more and more pronounced. Right. So this nonlinear scale K and L is really the most important thing, which again, as we go earlier times, smaller scales. Right. That's really the key of this picture. And so naively, you see that this is kind of the problem, right? Naively, what I want people to have in mind here is that it seems that we're losing a lot of momentum, like a lot of physical scales in our picture, just because we have to really abide by the radius of convergence. That naively seems like a problem. Before I get to how much of a problem that is, though, I want to establish the baseline model I will use in this talk, which will be the evaluation of the 2-point function of matter clustering at 2-loop order in the EFT. Of course, this expression has many, many details, which I won't go into, but I just want to highlight roughly kind of the picture we've been discussing. So the CS squared here term is a sound speed term, very much like I was showing for the case of water. This is the leading order sound speed term. This fluid turns out to have a non-trivial time dependence, so it has hysteresis compared to fluids like water, which have a very fast relaxation time. So you also have to include, for example, a sound speed at next leading order, which captures the time dependence of the sound speed, and then there are also higher orders. There are also higher order derivative corrections and higher orders in the stress tensor. And if you go to for example, if you go to 1 order lower in the theory and 1 loop in the perturbation theory, then the only correction you have to include at that order is this next leading order sound speed. But okay, the total expression is not terribly important, and this asterisk here indeed means that I've actually dropped many terms because it turns out that many of these terms are somewhat degenerate theoretically, and so typically when we do these analyses, we don't include all of them. For example, I've here only included 2nd order in the stress tensor, but in fact, there's also a 3rd order which I've dropped. I can go into all the details if you want later, but it's a bit annoying to discuss to describe during a talk. But okay, I mean, the real question after all this is does it work? And of course, the answer is yes. Here at redshift 0 is a comparison of the matter power spectrum to a fully nonlinear simulation, and you can see it really matches the simulations. A very, very high precision simulation in this case, one of the most extensive simulations ever run, I think, at a really sub-percent level. And what you can see, actually, I want to point out 2 things. So this curve over here is linear theory. So you can see we're really doing much better than the leading order. But also, if I don't include these fluid parameters that I derive from the EFT that capture the small scale behavior, the 2-loop prediction without these 3 parameters looks like this curve here, and it does actually worse than the linear theory. So it's really critical that we understand, we use this fact that the small scales back react into the fluid parameters in more scales to capture this behavior. And then as I go to higher and higher redshift, the colors here include redshift, I can actually fit to progressively smaller scales, as you can see. This black line again is the error on the simulations, but you can see that as I go to higher and smaller scales, I can really do quite well. And more than that, these solid lines here are showing my fit if I let these EFT parameters, that is, if I let these free parameters over here be smooth functions of time rather than being fit for each individual data point. And you can see that actually does more or less as well as you would do if I fit for each individual data point, which means I'm really fitting for some physical parameters that are evolving over cosmic time. But of course, what you will also take away from this picture is that this is really a far cry from the behavior of n-body simulations that can go through all of these scales. Right, we're really still very, very far away from being able to capture all of these scales as in n-body simulations. Even as I go to higher redshift, eventually things break at around K1.
What is the gray area in the
Here,
around
this is some theoretical error that is estimated for the
true loop?
Yeah. No, I wouldn't take it too seriously. I think
Yes.
that mostly gets with that.
But the seeds that you have there are fit to the simulations, or
They are fit. So they have So they have to be fit to data. They cannot be. They cannot be derived from first principles. So
Yeah.
in the same way that like the sound speed of water cannot.
yeah, right? Okay.
Yeah. But you see, the fact that they are very smooth functions of time is actually evidence that we're not overfitting, right? That there's a smooth evolution of these fluid parameters over time.
Yeah.
What's your free parameters? To fit in like an effective theory, I would expect to have more and more degrees of freedom within the two.
Yeah. So these are the free parameters in this case.
All these C1s or
Yeah.
okay.
And these are the Wilson coefficients. At two loops, these are the one that one loop is only this one. And you can see, by the way, that at one loop it does pretty well, but it does better than linear theory. But it clearly also the screen curve is the one. The next one is one a bit worse. So
They're being very unfair, right? Wonderful.
I'm being unfair.
Yes, I think it's going up to 0.1 there.
But that's because it's matter, right?
Okay, it's not that, but it's not that bad, right?
It is. It actually. It is.
So it's the liberty of the biases.
Yeah. Here there's no bias. Yeah. Here is the fact that.
Yes, I know.
So in fact, as Alejandro was alluding to, we in fact use one predictions now as a matter of course for studying spectroscopic surveys, just to show that there are other cosmological contexts where things have worked. And in fact, for standard analyses, we've really shown over the past 10 years that even at one loop in perturbation theory, we can essentially match the statistical requirements of current and probably all future galaxy surveys. Now, I myself have worked in the so-called, actually Alejandro as well, has worked. We've worked in the so-called Lagrangian EFT functional structure. But there are many codes as well. And here, what you can see here is that many different slight variants, slightly different flavors of the EFT, and slightly different frameworks really agree with each other very well, much better than even the statistical error our simulations get at really the sub-percent level. And this is not just from the power spectrum, which I'm describing here, it's also from the bispectrum. And for year one of the DESI survey, myself, Alejandro, and students really worked, really did these kind of really precise comparisons between different codes, including my code, velocimeters, and Alejandro's code, FOPs. You can see that we really got we are able to go from these theories to obtain very, very consistent and precise and well-controlled constraints on cosmological parameters. I forgot my little advertisement here. But yeah, I mean, obviously, also include the work of Hernan, who's in the audience somewhere. But yeah, I mean, I think our experience in spectroscopic surveys has really been convincing that we can really use these analytic techniques to study the clustering of galaxies in fairly precise ways in this picture. But now to come back to Alejandro's question, one thing I've ignored is the elephant in the room. Of course, is baryons. Of course, all elephants are made of baryons. But what I've neglected so far is that the effects of baryonic feedback are actually very important for people. What I mean by that is as I go to smaller and smaller scales, I go from scales where gravity is the dominant force, that gravity is the force shaping all of all the clustering dynamics, to scales where baryonic feedback, gas dynamics become very important. Then even stars where they're a star. And this is a very important effect to take into account in our predictions as we want to go towards smaller scales. Of course, in analytic theory, the EFT does not care what the ultraviolet theory of the fluid is. So in the EFT, all that happens when I have baryons is that I change the fluid parameters, which in any case I fit. But if I were to run a simulation, I can no longer rely on purely gravitational simulations, so-called n-body simulations, but I'd rather have to go to hydrodynamical simulations, including all these baryonic processes, right? I mean, the n-body simulations are purely collisionless dynamics. I go to collisional, very complicated dynamics when I include these hydrodynamical effects. But these simulations, it turns out, are very, very expensive, much more expensive than even n-body simulations, and very poorly understood at the percent level. In fact, you can see from the summary of different hydrodynamical simulations in the market that they differ at small scale and far more than the percent. So this naively also presents now a kind of impediment to using n-body simulations purely, right? Because how can we do a 0.5% cosmic shear constraint when my n-body simulations differ by 20%? So I think that that's really another motivation for trying to see if we can make progress on an analytic theory where we don't have to depend on these precise on fully solving the problem of hydrodynamic astrophysics. So the question now is cosmic shear perturbative, right? Is cosmic shear perturbative? That is, are the modes that we can measure within the two-loop EFT enough? Right. So, and I think the answer really is made. That is, if we swallow the bitter pill that we cannot model baryonic feedback from first principles from hydrodynamic simulations, then the modular parts that you can get in n-body simulations anyways are already modes that can be probed by the two-loop by analytic prediction. And so here you can see, for example, there's a red line here is the cut that DES had to make already using their current data. So this cut was made by saying, if hydrodynamics are indeed what they look like and can produce a big contamination into cosmic shear, what scales do I have to cut at current error bars that I will not bias my constraints? They have to cut here. Compared to the amount of the signal that is coming from the perturbative mode, which is this blue line here, and the total signal, what you can see is on the modes that DES can keep, these are the cosmic shear signal is actually very, very perturbative. So once I take into account the fact that weak lensing is coming from these, that weak lensing is fundamentally limited by baryonic feedback when you use simulation analyses. Once you accept that, then most of the weak lensing signal is actually coming from modes that are modeled by analytic methods, and so that I think really gives us the motivation to push forward to try to see if we can understand weak lensing from this perspective. But of course, then we still need to understand how to do this number. But again, we're still in a situation where the matter power spectrum evaluated at this physical momentum is being integrated over many, many distances. So still, it seems like naively we have to do an integral to k of infinity, which is not well behaved in our theory. Right. So how do we do this? This brings me to the next portion of the talk. Right. So again, I want to remind us of this physical picture where fundamentally our physical theory now works up until some scales and cutoff, where now the cutoff is either the linear scale or the baryonic scale. And so you can see that actually this is also a problem for a simulation, right? In simulations, I also have to do this integral, bearing in mind that this integral has to include scales that my n-body simulation cannot do. So how can I consistently do analyses given a physical cutoff in angular space? Right? I think that's the question that I want to answer. Right, and in fact, I would say that this question is not just of academic or mathematical interest. Back in ancient times, when I first started working in cosmology, people were even more worried than they are now with the SA extension. It seemed much more serious. And one insight that emerged from all this discussion was that actually the measured lensing amplitude S8, or constraints on weak lensing, were actually very sensitive to small scales. So there's this paper, which, okay, they used a somewhat strange empirical model, but they showed if I let the nonlinear clustering amplitude of dark matter to vary as a free parameter rather than being fixed by theory, then this parameter is very, very degenerate with a weak lengthening amplitude. And in fact, you can translate such a thing into a prediction for what the shape of baryonic feedback has to be. And so people began to be worried that maybe we were seeing low lensing amplitudes because baryonic feedback was stronger or more different than we thought. And this actually has turned into a somewhat interesting. I'm worried if I click this button, it will kill. Oh, go ahead. Okay. So I think this has turned into a kind of a fruitful area of research where people have tried to use various ways to constrain baryonic feedback through astrophysics. For example, here by measuring the kinetic Sonoyev-Zldovich effect around density galaxies. But I would say that these things are still kind of far from analytic theory in the way that it's quite hard to translate between these directly and what baryonic feedback actually looks like. So, I mean, this to me really suggests that we need to go beyond having to have a complete and first principles theory of galaxy formation to do weakling, right? And the solution to this problem, I think, is that we really should not need to know the UV theory of galaxy formation to do weak lensing. In fact, small-scale contributions to weak lensing should not be arbitrary, right? That we should, the lesson of the EFT, if we have a physically well-posed parameter, we should be able to understand what the sensitivity of this observable, this physical observable from the small scale is. And so now I want to see if we can understand what this description should be, right? So remember, I want to look at this integral in the limit that the distance chi goes to 0, and that is at the distance the momenta goes to infinity. Right? In particular, I want to understand what are the contributions of the integral when this guy k over here, L over chi, goes beyond the physical scale lambda. Okay. I will skip this so you get the picture. There should be a simple form. So, in fact, we can do the simplest limit. So, in the limit, as chi goes to 0 in the lensing kernel, the lensing kernel for any sample of galaxies is linear in the co-moving distance chi. Goes to this that. And so you can see, for example, in DES, for all their galaxies, you can see that all these curves converge to a straight line at very, very low distances. So we can ask the question, okay, what does the small scale contribution to weak lensing look like? The limit that the lensing curve looks like this. And of course, now, given that k equals L over chi, we can do a very simple coordinate transformation that d chi and dk are related in this way. Of course, it's just a rule of substitution. And so when we do this integral, we can see that the leading order in a small scale contribution, the leading order counter term to lensing is something that looks like this. This is just a slope times L, right? Times this integral of the matter power spectrum for all scales k greater than f, right? So what this tells us is indeed that the leading order contribution of small scales to the weak lensing power spectrum is not some arbitrary shape, but rather a very smooth and linear function of the angular scale. And this free parameter is characterizing exactly the small scale behavior of the matter power spectrum. And that, I think, is really the main takeaway. So if we define now the so-called lensing counter, which given some particular UV completion is this number, this integral of the matter power spectrum, what you can think about is that if I have a pixel in the sky where I've measured the weak lensing, this term captures what the noise fluctuations due to modes that are smaller than my cutoff look like. Right? They're really capturing in this
That's a function of C, right?
Of Z?
That is also a function of redshift. You
Here,
go back one slide.
Yes, but here I'm expanding on chi goes to 0. So this is the leading order in the Taylor series. I'll come back to this section. Right, so we're really thinking about the noise due to UV modes in each pixel of our weak lensing. And this is very much for aficionados of galaxy clustering. This is very much like the shock noise in each voxel of your galaxy map due to the stochasticity of galaxy clustering, but now in a two-dimensional weak lensing context. And in general, of course, we can expand the weak lensing integral to smaller and smaller scales. And when we do this, of course, I won't go through all the math. When you do this, what you find is that every single weak lensing observable can be expanded through a series of consistent intervals of the matter power spectrum involving also its time difference. But the point of this equation is that the coefficients of this thing are completely fixed given the matter power spectrum. That is, every single weak lensing observable, whether it be CMB lensing, weak galaxy lensing, all these things, for any sample, share the same lensing characteristics and capture the UV sensitivity to matter clustering at small scales. And so it doesn't matter how many weak lensing observables you have. You really always have a finite set of free parameters in this renormalized picture of weak lensing that we have. I'm past them.
So you're getting rid of the C dependence on the content of the power spectrum.
No, this is the time dependence of the power on small scales, but there is Z dependence.
Okay, you're going to tell us how to deal with that.
Yeah. So just to show how this works, if I take a universe where that agrees with simulation, I can compute what these lensing counterterms are in practice, and you can see that adding in lensing counterterms significantly extends the range over which we can fit. Right. So anything that's left over from these curves in this black dashed line that do not include the colored lines are the pieces of the model that are coming from the perturbative mode, while these lensing counterterms are soaking up the UV dependence theory. And what you can see here is that if I naively say that I want to make a cut where my model hits 5% of the UV contribution, I would have to stop at a very large angular scale. Whereas when I take into account the smooth dependence on the small scale, I can go to smaller angular scales. Just to show that it works. And the really interesting thing to me is that when we use kind of effective description of the data, even as I added more and more free parameters into the theory, what I actually get is a significant improvement in constraining power. When I do cosmological observables here, the different curves are as I go to higher and higher order in this expansion of the lensing UV sensitivities. And what you can see is that even as I added more parameters, my constraining power is increasing, and this is because I can go to smaller and smaller scales. And as I properly account for the UV sensitivity. And so we can really think of adding these counterterms as a way of turning a physical scale cut into a theoretical error that I have to fit over my lensing observable. And you can see that it'll be particularly powerful for future surveys like Rubin LSST, which have a lot of power, constraining power on small scales, where you can see really factors of several improvement when I do concentration. And finally, just to show that this method actually works, I came up with the following physical scenario. Suppose that dark matter were not closeness dark matter, but rather were rather fuzzy dark matter or a super ultralight accent dark matter. In this case, the power spectrum at a very small scale is suppressed compared to lambda CDM, compared to Santa Monica cosmology. And I don't account for this in my cosmic shear fits. I'll get a very, very biased result. But if I properly include the effect of this UV sensitivity into my model, then you can see that these counterterms account for this non-fluid behavior, the quantum behavior of the fluid at small scales, and allow me to recover the true cosmology while picking out the fact that the lensing counterterm is quite a bit different than what you expect for lambda C and the true. So you can see is that this model is actually able to pick up. This model is actually reflecting these fits. The data are actually reflecting the fact that there's that we have control now over this whole thing. I think I'm running out of time. So
this is a K, very large K, right?
In this case, this is like K of like 1-ish. Yeah. I mean, it's really a very, very small axion mass.
K of 1? It's larger than 1, right?
No, I mean,
I don't know.
For this mass about 1, you can pick whichever, depending on which mass. Yeah, I mean, it depends on the mass, right?
Yes.
So just to finish off, just to finish off, I think maybe I'll skip this part. I mean, there's another part which is that the shapes of the galaxies are not actually fully random, but have their own correlation called intrinsic alignments. And we can actually also model these using the EFT. In this case, we actually have to come up with spin 2 operators, which have a very interesting structure, but I'm going to skip discussing this because I think we're out of time. But now I want to show that using the methodology, these two pieces of effective field theory thinking I've discussed. First, the EFT prediction of the matter power spectrum at two loops. And secondly, doubly, the effective description of the data to these lensing counterterms. I can now actually conduct a full analysis of weak lensing data only purely analytically. Actually, I skipped this. I actually skipped one slide in my. So, yeah, actually, let me skip this slide. Let me skip this slide too. So yeah, so we can actually do a fully analytic fit to the data, in varying scenarios, right? So we can do it from lambda CDM. We can add in data from BAO, for example, big lambda statistics. But what I think is really interesting actually is that we can conduct analyses of weak lensing now for the first time fully nonlinearly in a W0 WA CDM and a dynamical dark energy scenario without any input from simulation. In fact, if you look at these same data, the DES data analyzed by the collaboration, they have to cut to very large scales because they don't have emulators that have dynamical dark energy or simulation that covers this range. And so they essentially have to use linear theory in very large scale. Whereas when we do it in the two-loop way, we are actually able to do this analysis purely from first principles with essentially no extra steps. So I think this is really a proof of principle that we're able to do weak lensing analyses competitively or even better than the state of the art. And one thing I want to point to is that you can see that this S8 that we get is one fully consistent with the S8 from the cosmic microwave background, so this dash line here. But the other thing I want to point out is that this error bar is actually very, very close to the error bar we get if we use a simulations-based analysis using emulators. And this is precisely because once you account for the fact that baryons have a non-negligible effect, your constraints using an emulator, using simulations, are already limited by scale that baryonic effects are. Right, so we're not actually losing any constraining power essentially by using only the perturbative theory that has a more finite radius of convergence.
Are these convergence maps or the shear?
Sorry, by convergence I mean
Okay,
the theory.
constructed convergence maps.
Yeah.
So,
These are DESY3 emotes.
actually, so, okay, these are the shear.
Yeah, this is shear.
Okay.
Yeah, this is a shear. As to my knowledge, to my knowledge, this is the first time people have been able to do a fully nonlinear W0W analysis theory, right? So I think this, the extension of this is really to say that once we have this analytic theory, once we have the analytic theory for a given extension of the standard model, we can really directly do these analyses without having to run very expensive simulations, which may not even converge level of the right? And so just to close off, I just want to show you, these are for mock data now, I just want to show the importance of both of these effects. So the blue curve is our full predictions given our scale cuts for C kappa, the lensing power spectrum. The orange curve is what happens if I use two-loop theory, but without the lensing counterterm, so without the EFT the data. And the green curve is what happens if I use the lensing counterterm, but don't include the EFT parameters in my fit. You can see that all of these things are really crucial to fitting the data at the error bars that the theory requires, that the data required. And that's what I mean by a doubly effective view of weak lensing, right? We're really an EFT of the data through the lensing counterterm and an EFT of the dynamics through a two-loop prediction of the. Okay. I will end here. So in conclusion, I'll just leave it up. But I hope I somewhat convinced you that cosmic shear is really roughly perturbative, and that simulations are no longer the only game in town. And we can really begin to think about even extensions to just lensing power spectrum, including extensions of galaxy clustering, higher order statistics, and so on. And broadly, I think we want to think about how to close our physical modeling of weak lensing, right? For the EFT, we can do this by working up to KNL with lensing counterterms. For simulations, of course, we have to stop at K baryons. And in the K lensing power spectrum, we can see a lensing counterterm fill a gap. But I think we really need to think about how we can do persuasive cosmology using cosmic shear that is not subject to questions like, did you account for baryons correct? Right? How we could do this in kind of really a first principles type way. And just to close, I want to mention that I think that really the future for this kind of thing is very bright. future surveys are going to higher redshifts and larger areas, which means that we'll have access to way more perturbative modes, while the limitation on small scale by bearing on this. So, I hope that is somewhat convincing, and thank you for having me, and then have to take any questions.
Questions?
Yeah, I'm not a cosmologist, but you showed that observable receives contributions from very large different scales, like very large, very small scales. Like as a particle physicist, I would expect that your perturbation theory is in trouble. Like in particle physics, something like the organizational equations is something that we get.
Yeah. Yeah, I mean, we can. I mean, in this case, I mean, in this case, I mean, we're really being controlled by this. I mean, the physical cutoff of the theories came in. And this, I mean, people have looked at. I mean, people have looked at running the theory, the cutoff, but I don't think it's. I mean, there's not really. I mean, all the parameters we put in are kind of dimensional parameters. It's not like the running gives you anything. So the other problem is that the input power, the propagator in this theory is a very complicated function rather than like a power law. So the running, there's not really like law to extract from. But people have looked at, one example you can do is you can compute these loop integrals in universes where the propagator is the linear power system is just a power law. I mean, you can kind of you can get a better control over what the parameters are in this case, because then there are no scales. But the conclusion is more or less the same. I mean, the power law in our universe, I mean, the power law in our universe is pretty close to a power law-ish on perturbative scale. So I don't know how to explain, but it's a kind of an ugly picture because it's particularly the shape of the power. And I have not mentioned that actually the perturbation theory parameters of our theory are actually, it's not just the counting of the, well, this is for many EFTs, but the counting is not just in the powers, the number of loops, but rather different loops can have different sizes because of the particular modes that data are sensitive to. And this is something we have looked into, but yeah, we can discuss it instead of too complicated this thing. Don't do much detail.
Another question? Other questions online? Well, I would like to know how do you determine the maximum K that your theory is valid, and does it evolve too much if one loop to two loops?
Yeah, this is a difficult question to which I will have an unsatisfying answer. So the best way we can do this really is, I mean, there are two ways when we manage doing this. One way is to compute the next order prediction and see how big it is. It's kind of the great management here. But this is not so great because, of course, we do not currently have a full 3-loop EFT prediction for this theory. So of course these are guesses, and so they're liable to be wrong by like a factor of 2 pi or whatever. The other way, which is typically what we use, is to fit the simulation. And that's the path we've taken here. Given that we have a sort of nonlinear realization, because we just compare the simulations to see how far it goes. And then we have to use some scaling arguments to guess that the fluid parameters will not be changed by some amount compared to if you have bearing on. But I think that's really kind of the only way. I mean, the rough scaling is in powers of K and L. And of course, you can always do a conservative analysis by just cutting out K and L or subtracting K and L, and that, which is actually what I've done here, and that actually doesn't lose you very much constraining power. So I think that may even be, in principle, the intellectually most rigorous way to go. But practically speaking, we always do this. And it seems like we can. I mean, one way you can see that the K-N counting is not exact is that the 2-loop prediction works roughly to 2 times K. So well, of course, with each loop you have like a factor of like 4 pi or whatever. It's present these, but It's not. Yeah, I mean, it's a somewhat inexact science exactly to which point material can work.
How do you deal with the redshift dependence on the conductors?
Yes. So this I've hidden it in this plot. So what we did is use a smooth spline over the redshift gradient that we proved with a.
So it's like pinning.
Yes. Yeah. It's actually exactly what we did for the BAO in year one of that. It's the exact same function. It's a binning with a fixed width that corresponds to the rough smoothness of the pattern.
Then how many parameters you have?
In this case, 16.
16.
So you can see that three is not enough. 4 is about right. So 4 times 4 counterterms is 16.
Second question.
Yes.
How do you compute the two loops?
Oh, brute force.
Brute force.
Yeah. In lambda CDM, it's very simple. I mean, people have been developing more faster ways to do the two-loop integrals. But in lambda CDM, everything is a function of just little omega CDM.
But it's a 5 integral, per dimensional integral, right?
Oh, well, you can do it. I mean, you can do it. I mean, the point is that
Yeah, but you can do it, but not for parameter inference.
so the trick. This is my clever idea is that in lambda CDM, of course, we cannot constrain NS or omega baryon from weak lensing, but the remaining two parameters are H naught and omega CDM. H naught is just an overall physical scaling, right? And omega CDM is once you fix omega CDM, the shape of the power source is exactly fixed. So all we have to do is evaluate the power the loop integrals along a 1D manifold of omega CDM. That's it.
It's a one-dimensional problem.
Yeah.
Okay.
So I think people have not realized it's a one-dimensional, but it is a one-dimensional. So you can do lambda CDM, just take
How long does it take each integral?
a couple hours.
The fit or the integral?
The integral.
A couple of hours.
Yeah.
Okay.
They're slow, but the fits are very fast. The integrals are slow.
Yes, this.
Yeah, but I make maybe 5 omega CDM points, and then it's no time at all, right? You run into one job in nurse case, but
Well, you have more parameters. Right? I want to continue mass, so
yeah, but it's not so.
it
Yeah,
will become complicated.
yeah, but then
And what happens if you have biases?
the biases are effective because the biases are just
I know,
Able,
but at some point you will want to do 3 times the point.
yeah.
So you will need the galaxy, all of that.
In that case, I think for a 3x2 point, you really only need a 1 loop for galaxies because the galaxies are at very particular physical scales, right? So most of the information will be there. I mean, we could do the 2-loop thing, and I mean there are ways to do the 2-loop integral faster.
Yeah, but this will be a okay, it's super nice. Everything looks super great. This would be a problem when you want to move beyond lambda CDM. You will have to do more integrals.
But I mean, you can use this like Cobra thing.
Yes, I was thinking.
Yeah, I think that would be fine. I mean, this is just to show what we can do it. I think there are once you see that you can do this analysis this way, then the details are just how
Technology will come.
Yeah.
Okay.
I mean, the technology almost is here anyway. So I think.
Yes, I know.
Yes, I think.
A general comment.
Yeah.
So your formalism doesn't solve the sigma tension because you are obtaining more or less the same here. From the beginning of your talk, I was thinking that you could solve something like that. But it's not the case.
No, I mean, no, I mean, the data will give what essay they want. Right?
Yeah, right.
But I mean, I think this is what I want to frame this as this is a way to measure S8 without having to worry that your S8 measurement is being biased like that.
Mhm.
And that I think is the main advantage. I mean, it is true. I mean, I think this is purely accidental. I mean, it's really purely accidental, but I mean, it is true that our S8 values are higher than what the official analyses give. But okay, I mean, that could have gone either way. It's not intended to solve the problem. It's just intended to give you a more robust answer. And I want to point out, I mean, here, we also did this analysis using a lensing counter, but using a dark matter, using an emulator. And here, in this case, we also got a somewhat higher S8 than the DES on the same data, but not much but really quite similar to the tulip one. And you can see actually that even when we cut to significantly larger angular scales, K of 0.5, which is much of a larger scale than DES ever does, or than any of these lengths ever does, we still get. I mean, then we get a somewhat lower SA. So I think there probably is something in the data that that the longer modes in the data do have a slightly smaller clustering amplitude, but they're still consistent. It's hard.
Just other questions? If not, let's thank Steven.
Thanks.